the weight you carry without knowing. There is something pressing on you right now, not in the way a hand presses or a thought presses, or the kind of pressure that arrives with bad news and stays. This is quieter than that. It is the kind of pressure that has no opposite, no moment before it when the pressure was absent, no future moment when it will be gone. It is simply there, in the space between your body and everything your body is not. You're lying down, probably, or close enough to lying down that the difference doesn't matter. Your weight is distributed across whatever surface is holding you, and somewhere in the room, between you and the ceiling, between you and the wall behind your head, there is a column of space that has never, not once in the history of this universe, been empty. It only looks empty. That is the first thing. The second thing is harder. That column of space, the ordinary air and ordinary nothing between you and the ceiling, is heavier than it was 1 billion years ago. Not because anything has moved into it, not because dust has collected or the air has thickened. It is heavier because the nothing itself has weight, and the nothing has been accumulating very slowly, measurably, in a direction that has no name in the language of rooms and ceilings and the ordinary hour you're keeping right now. This is not a metaphor being built towards something cleaner. The weight is real. The accumulation is real. The measuring of it required some of the most careful science of the last century, and produced, as careful science sometimes does, an answer that nobody wanted and nobody could argue with. Sit with that for a moment before anything else. You have a body. Your body knows certain things without being told. It knows the difference between a room that is occupied and a room that is not, even when nothing in the room has moved. It knows when the air has changed before the nose confirms it. It knows, at some level below thought, that space is not neutral, that it has texture, that it pushes back in ways too subtle for waking attention, but not too subtle for the part of you that registers things while the rest of you is somewhere else. That part is not wrong. It is picking up something real. Physics, when pressed, will tell you that a perfect vacuum, a volume of space from which every particle has been removed, every photon chased out, every thermal vibration cooled to absolute silence, is not empty. It cannot be empty. Something remains when everything else is gone, and that something is not nothing, and it has energy, and that energy has consequences that run from the smallest scale imaginable to the largest scale the universe has managed so far. The consequences, summed across the void between galaxies, across the dark oceans of space where no star has ever burned and no planet has ever turned, add up to something that is quietly running the universe. That is where this is going. But not yet. Right now the question is simpler. It is just, why does the space between things feel like something? You have probably never asked this question. Most people haven't. Space is the container, the context, the absence in which presence occurs. It is what you move through without thinking about. It is the part of a painting that isn't paint. The idea that it might be a substance, that it might have properties, that it might participate in what happens rather than simply hosting it, runs against something deep in how the mind prefers to organize experience. There is stuff, and there is where stuff is. The where doesn't get to have opinions, and yet. The where has been having opinions for the entire life of this universe. It has been pushing back against gravity with a force that grows as the universe grows. It has been contributing to every calculation any physicist has made about why galaxies move the way they move, why the universe is the size it is, why the rate at which everything is flying apart from everything else is not slowing down the way gravity demands it should, but is instead. And this is the fact that upended 3 decades of cosmology in the space of a few years, speeding up. The empty is winning. Here is what that means in terms you can hold for a moment before setting down. Every second, the universe is larger than it was the second before, not because anything is moving through space. The galaxies themselves are largely staying put relative to their local neighborhoods, but because the space between them is stretching, growing, adding distance between things that have not moved. A meter of intergalactic void becomes, in time, 2 meters, then 10, then 100, and the force driving this is not coming from anything in the galaxies themselves. It is coming from the space in between. The void is driving its own expansion, and as it expands, the pressure, if you want to call it that, does not thin out the way everything else does. Pour ink into water and the colour spreads and fades. Fill a room with warm air and open a window, and the warmth disperses and is gone. Every substance, every force, every form of energy that physics knows about gets diluted when the space it occupies grows larger. Except one. The energy of the void maintains its density. More space is created, and the energy per unit of that space does not drop. Which means as the universe grows, the total energy of the void grows with it. It is not conserved in the way you were taught things are conserved. It does not spread from where it was to where it wasn't. It appears in the new space fully formed at the same density it was before. This is the part that should feel strange. If it doesn't feel strange, it is worth sitting with it until it does. The pressure between you and the ceiling is, in a very precise sense, the same pressure driving the universe apart. Not the same magnitude. You would need many billions of light years of void to accumulate anything that a scale could register, and the room you are in is not a billion light years of void. But the same phenomenon, the same energy, sitting quietly in ordinary space, doing what it does at the density it has always had and will always have. It was there before the room was built. It was there before the planet was there to build rooms on. It will be there after the last star in the last galaxy has gone cold, and the universe has stretched so far that even light from neighbouring galaxies can no longer reach us. The void is not waiting for something to happen to it. It is the thing that is happening. You are resting in it right now. The chapter ends here not because the idea is finished, but because this is enough to carry forward. The pressure has been named. It has not been explained, not yet, not fully, and in some ways not ever, but it has been named. And the name changes something about the weight of the dark between the objects in this room, which has not changed, which has always been exactly this heavy, and which you will perhaps notice now for the first time as you drift. Before the void, had a name start far enough back and everything looks like a map drawn by someone who only cared about the roads. For most of the time that humans have looked at the sky seriously, with instruments, with mathematics, with the particular patience that science requires, the dark between stars was the dark between stars, and that was the end of it. Maps were made of brightness. Catalogues were built of things that shone. The universe, as far as the tools of astronomy were concerned, was a collection of luminous objects suspended in an undifferentiated background, and the background was, by definition, by assumption, by a silence so complete it had never been questioned, nothing. Nothing was not a category that required investigation. Nothing was the default condition against which everything else was measured. You mapped the fires and ignored the night. This is not a failure of imagination particular to astronomers. It is what attention does. Attention goes to what is there, to the distinct, the bright, the countable. The in-between is where attention rests when nothing is demanding it, which means the in-between is, for practical purposes, invisible. The space between the furniture in a room is not what you see when you walk in. You see the furniture. The space between is just how far you have to move to reach the next piece of furniture, and no one catalogues that. For centuries, the universe was furniture. What changed was not the universe. The universe has been doing exactly what it does for 14 billion years and has no particular interest in human categories. What changed was the accumulation of small anomalies, the slow, uncomfortable building up of things that didn't quite fit, and the willingness, eventually, of certain physicists to take the anomalies as seriously as the objects. The anomalies did not arrive dramatically. They arrived the way most important things arrive, as slightly wrong numbers in otherwise convincing calculations. Newton's gravity worked. It worked so well for so long, across so many scales, that its working became a kind of background assumption, the way the dark between stars was a background assumption. Planets moved exactly where they should move. Tides behaved. Cannonballs obeyed. The solar system was a machine of exceptional precision, and the machine's manual had been written in the 17th century and confirmed by every subsequent measurement. There was no reason to think the manual was incomplete. Then the galaxies started moving in ways the manual did not account for. Not dramatically at first, not in a way that announced itself as discovery. More the way a clock that has been running slightly fast eventually, after enough accumulated minutes, shows you a time that cannot be right, and you look at it and think, something is off. The galaxies were moving too fast. Not all of them, not in every direction, not in a way that could be explained by the visible matter in them. There was more gravitational pull than the stars and gas could provide. The manual said the numbers should be smaller. Something unseen was pulling, something that did not shine. Dark matter is not the subject of this chapter, but it belongs in this sentence because it was the first hint that the dark between things was not passive. It was the first evidence that space was not simply the container in which luminous things happened, but was itself a place where things could be present without announcing themselves, could exert force without being visible, could be real in the full physical sense without being findable by the tools that had been built to find things. Something was there in the halos around galaxies, in the spaces between galaxy clusters, pulling with the patient indifference of mass that has never needed to be observed to do its work. And then the map, already complicated by this invisible matter, acquired a second complication, deeper and stranger, and still not fully named. The universe, it turned out, was not just full of invisible stuff. It was also stretched. It was being stretched. Right now, continuously, in every direction, with a force that was not coming from any object in it, not from the dark matter, not from the galaxies, not from anything anyone had identified and catalogued in a century of careful observation. The force was coming from the space itself, from the in-between, from what the old maps had simply labelled as background. The background was pushing. There is a quality to the moment when a long-held assumption quietly breaks. It doesn't feel like discovery, not immediately. It feels like disorientation, the specific disorientation of a room that has always been arranged one way suddenly being arranged differently, where nothing is missing but nothing is where it was. The room is still a room, the furniture is still there, but the space between the furniture has rearranged itself, and you cannot quite get your bearings. This is what cosmology went through in the years around the turn of this century. The objects were still there, the galaxies, the clusters, the ancient light still travelling from the first moments of formation. The measurements were good, the instruments were better than they had ever been. But the space between the objects was behaving in a way that the existing map could not account for, and the space between the objects was everywhere, which meant the map was wrong everywhere, which meant something fundamental had been quietly wrong for as long as anyone had been making maps. The disorientation settled over time into a name, dark energy, not because anyone knew what it was, because it needed a name the way an unidentified sound in a house at night needs a name, not to explain it, just to keep it from consuming too much of the mind's available space. Call it something, and you can set it aside long enough to keep working. Dark energy. 68% of everything. Here is what the name contains and what it doesn't. It contains the observation that something is causing the expansion of the universe to accelerate, and that this something is distributed uniformly through space, not concentrated in galaxies or clusters or any identifiable structure, but present at the same density everywhere, in the void between galaxies as much as anywhere else, which is to say most present in the void because the void is most of what there is. It does not contain any agreement about what this something actually is, whether it is a property of space itself, a term in the equations of general relativity that Einstein added, removed, and was eventually found to need, or whether it is a field that moves through space, or something else entirely that does not yet have a framework adequate to hold it. The name is a drawer into which a problem has been placed while the room is tidied. The drawer is still closed. What astronomy lost when it stopped treating the dark as background was a kind of simplicity that had been comfortable for a very long time. The universe of luminous things, catalogued, measured, mapped, was a universe that rewarded the approach of going toward brightness, that confirmed the instinct to pay attention to what announced itself. That universe is still real. The galaxies are still there. The stars are still burning. But the majority of what exists is in the drawer. More than 2/3 of the energy content of the universe is something that cannot be seen, cannot be directly detected, does not interact with light, and lives most fully in the spaces between the things that can be found. The night sky, the dark between the constellations, the immeasurable ocean of void between the nearest galaxy and the next, all of that is not absence. All of that is where most of what is. The map has been redrawn. The background is no longer background, and the dark, which was once simply the dark, is now something the instruments lean toward, trying to read in the way you lean toward a sound in another room that may or may not have been what you thought you heard. It's still there. Whatever it is, it's still there. And the leaning continues. A jar that keeps getting bigger. Somewhere there is a volume of space, not a large one, 1 cubic meter, say, chosen at random in the void between galaxies, a region so empty that it makes the emptiness of ordinary space look crowded, a region where even a single stray atom would be a notable event. Nothing is in it. That statement is already wrong, but set that aside for now. The volume expands, not because anything pushes the walls out. There are no walls, but because the space itself is stretching, and this particular meter of space is stretching with the rest. It becomes 2 meters, then 3. The shape is arbitrary. Call it a cube for convenience, though space does not organize itself into cubes for anyone's convenience. Watch what happens to what is in it. If there were ordinary matter in the cube, a gas, a handful of atoms, those atoms would dilute as the cube expanded. More volume, same number of atoms, lower density. This is what gases do. This is what everything does when given more room. You spread out. The density drops. Eventually, given enough expansion, you approach something that is not nothing but behaves like nothing on any practical measurement. The cube does not behave like this. The cube keeps something inside it that does not dilute. As it doubles in volume, the energy it contains also doubles. Not because anything flows in, not because energy is travelling from elsewhere to fill the new space. The new space arrives already full. It is full of the same thing the old space was full of, at the same density, in the same way. This is the thread. Follow it. New space, made by expansion, with energy in it that was not there before and did not come from anywhere. That is the sentence this chapter is pulling on. That sentence has a physics name, the cosmological constant, the energy of the vacuum, and a measurement, and a place in the equations, and a history of being inserted, removed, and found again. But none of that is the thread. The thread is simpler. Where does it come from? There is a long, quiet middle here where the honest answer is, nobody knows. This is not the kind of nobody knows that means we haven't gotten around to it yet. It is the kind of nobody knows where the calculation that should give the answer, the calculation that sums up the quantum mechanical energy of empty space, gives a number so different from the observed value that the disagreement is not a rounding error. It is a problem so significant that the physicists who understand it best describe it with words like embarrassing or catastrophic, or the worst prediction in physics. The prediction is too high, by about a factor of 10 to the power of 120. This fact sits in the middle of this chapter without being cleaned up, without being minimized, without a sentence following it to make it feel more manageable. It is not manageable. It is an open wound in the center of cosmology, and the strange thing is that the universe does not care. The universe keeps expanding at exactly the rate the observed cosmological constant predicts. The expansion is measured, confirmed, consistent with itself across a dozen independent methods. The universe knows what value to use, only the calculation is wrong, enormously, mysteriously, enduringly wrong. Set that down now. It belongs in a later chapter where it has more room. What the thread is following is not the discrepancy. The thread is following the newness. When the cube expands from 1 meter to 2, the extra meter of space is, in a precise sense, new. It did not exist before. It was not transported from elsewhere in the universe, redistributed, shuffled around the way matter shuffles when systems equilibrate. The expansion of space is not the spreading of a fixed resource. It is the generation of new volume, and the new volume comes with something inside it. This is not how the rest of physics works. All the other things in the universe obey conservation. Matter is neither created nor destroyed in ordinary circumstances. Energy is transformed but not made. The inventory of the universe is broadly stable, distributed differently across time, concentrated here and dispersed there, but not augmented by the act of things moving apart. The vacuum energy doesn't follow this, or rather, it follows a rule whose consistency is with itself rather than with the things inside it. The vacuum is not a substance that disperses. It is a property of space, and space is generating itself, and the property comes with the space, in the way that a certain temperature comes with the interior of a living body, not because the temperature flows in from outside, but because it is what the living body, being what it is, maintains. This is the closest analogy available. It is still not quite right. The thread does not resolve into something clean here. That is all this chapter is saying. The cube gets bigger. The content per unit volume stays constant. The total energy in the cube increases. The source of the increase is the expansion itself, which is itself driven by the energy. A self-sustaining loop, quiet and perfectly maintained, running in every cubic meter of void in the observable universe, in the vast majority of space that no instrument has ever measured and no light from any star has ever reached. The jar keeps getting bigger. The whatever it is inside the jar keeps pace with the jar. This matters because it is where new things come from, not objects, not particles necessarily, though the question of particles will arrive in its own time. It is where the ongoing life of the void comes from, the energy that is doing the stretching, that is accelerating the expansion, that will eventually, given enough time, stretch the universe so far that nothing can see anything else, in a darkness so complete that the word darkness doesn't capture it. That darkness is being built right now, at the same rate everywhere. The cube is still expanding. What the equations were too polite to say. The letter was finished in November 1915. Einstein sent it before he was entirely certain it was right, not from carelessness, but from the specific pressure of knowing that someone else was close, that the mathematics was converging from two directions at once, and that to wait for perfect certainty was to risk arriving second to the thing you had spent a decade building. The field equations of general relativity went out into the world, still warm, still slightly uncertain at their edges, and began immediately to pass every test anyone could construct for them. The test they passed first and most dramatically was the one nobody had yet managed. Mercury's orbit had been misbehaving for decades, precessing slightly faster than Newton's gravity could account for, the gap small enough to ignore and large enough to bother careful people. The new equations explained it exactly, not approximately, exactly. The value that had been wrong under one framework came out right under the other, and the difference between the frameworks was the difference between treating gravity as a force that objects exert on each other across empty space and treating it as a curvature, a geometry, a shape, that objects impose on the space itself. Space was not empty in this picture. Space was pliant, shapeable, responsive to what was inside it. It bent around mass. It told matter how to move, and matter told it how to bend, and the two were in constant conversation, and the conversation was what gravity was. This is the thing the equation said, and it was enough to occupy physics for a generation. But the equations had also said something else, something quieter, something that made Einstein uncomfortable enough to remove it before the work was published, uncomfortable enough to call it later his greatest mistake, and correct enough to be restored decades later by observations he would not live to see. The equations, unmodified, described a universe that could not hold still. Not because anything was wrong with the mathematics, because the mathematics, applied honestly to a universe full of mass, produced a solution in which that universe was either expanding or contracting. The mutual gravity of everything in it would pull it toward collapse unless something else was acting, unless there was some counterforce distributed evenly through space, pushing out against the pull of matter. Einstein added the counterforce. He called it the cosmological constant, a term, a symbol, a number that represented a kind of repulsion built into space itself, a pressure that existed everywhere at once, and pushed back against the inward pull of gravity hard enough to hold the universe in something like equilibrium. He had not discovered this term from observation. He had added it because the alternative was a universe in motion, and a universe in motion conflicted with what Einstein in 1917 believed, that the universe was static, eternal, fundamentally the same in all times as in this one. The constant was a correction, a quiet adjustment to make the equations agree with the universe as he imagined it to be. Then Hubble's observations came, then the redshifts, then the careful measurement of distances to galaxies so remote that the light arriving from them had been travelling since the universe was young, and those measurements showed not a static universe but an expanding one, not stillness but motion, every galaxy moving away from every other galaxy with a velocity proportional to the distance between them. The universe was not sitting quietly in the equilibrium Einstein had designed for it. It had been in motion the whole time. He removed the constant. Unnecessary, he said. An embarrassment. A mistake made not from wrong mathematics, but from the wrong prior. The assumption of stillness that the observations had now dissolved. The equations, left to themselves, had been right all along. The universe was expanding, and it needed no special term to explain its expansion, and the cosmological constant could be set to 0, and the physics would still work, and the observations would still be explained. This is where the story would have ended if the observations had stopped. The observations did not stop. They got better instruments, better methods, a new generation of astronomers with access to the Hubble Space Telescope and the ability to measure the brightness of stellar explosions at distances that previous generations could only estimate. And the better the measurements got, the more clearly a problem began to emerge, the same problem that had appeared before in a different form, the same kind of off number that means something is being missed. The universe was expanding. This was confirmed repeatedly to high precision. But the rate of that expansion, the relationship between distance and velocity that Hubble had first described, was not behaving the way a universe full of matter and nothing else would behave. In a universe where gravity is the only long-range force, expansion should be slowing. The mutual pull of all that mass should be tugging everything back, decelerating the outward rush the way a ball thrown upward decelerates in the gravitational field of the Earth. The measurement said the deceleration was not happening. The measurement said, quietly at first, then with increasing confidence, then with a certainty that left no comfortable escape, that the expansion was speeding up. The cosmological constant came back, not as a correction this time, as a discovery, as the measured, confirmed, reproducible signature of something that was pushing the universe apart from the inside, something that lived in the space between galaxies as a property of that space, something whose density did not change as the universe expanded, and that therefore, as the universe grew larger and the contribution of matter to the total energy budget shrank with dilution, was becoming the dominant thing, the majority thing, the thing the universe was mostly made of. Einstein's greatest mistake turned out not to be the introduction of the constant, but its removal. What he had added speculatively to preserve a static universe that turned out not to exist was the right term for the wrong reason. And the right term, once the universe revealed that it was not static, not decelerating, not behaving as gravity alone could explain, became the central fact of modern cosmology. This is what orbits around the center of this chapter without landing. The constant is confirmed, is measured, is used daily in cosmological calculations that match observations with extraordinary precision, and it is not understood. The number that comes from observations and the number that comes from the theory of what the quantum vacuum should contain are not in mild disagreement. They are in a disagreement so extreme that the field cannot simply wait for better measurements to resolve it. Something is fundamentally wrong somewhere, either in the calculation or in the framework that generates it, and nobody has yet found the wrong thing. The equations were too polite to say, we don't know why this is the number that it is. They just reported the number, and the number kept showing up in survey after survey, in measurement after measurement, in the motion of galaxies and the bending of light and the slow drift of the cosmic microwave background, steady and unreasonable and real. The constant is a number in a box, and the box is sealed, and the key is something physics has not yet made. Foam smaller, keep going smaller. Past the atom, which is already mostly space. Past the nucleus, which is almost incomprehensibly dense relative to the atom surrounding it, but which is still, at the scales that matter here, enormous. Past the quarks. Past whatever quarks are made of, if they are made of anything, which is a question that may not have an answer in the framework currently available. There is a scale, theoretical for now, called the Planck length. It is approximately 10 to the negative 35 meters. To give that number a shape, if an atom were scaled up to the size of the observable universe, a Planck length would be about the size of an atom. This is the scale at which the smooth geometry of space, the pliant curving space-time of general relativity, is thought to break down. Below this scale, the equations stop behaving. The smooth surface ends. What the equations suggest is there instead has a name: quantum foam. The name is doing more work than the theory can quite justify yet, and I want to be honest about that. What is known, what the mathematics of quantum field theory establishes with considerable confidence, is that the vacuum is not static at any scale. At all scales, fields are fluctuating. The electromagnetic field, the fields associated with every type of particle, All of them have what is called a ground state energy, a baseline vibration that cannot be removed even at absolute zero, even in perfect isolation, even in the most thorough vacuum that can be prepared. You cannot empty a region of space of this energy. It is not a thing that is in the space. It is a thing that the space is. These fluctuations are not hypothetical. They have been measured, in a sense. The Casimir effect, the tiny attractive force between two uncharged metal plates placed very close together in a vacuum, exists because the plates alter the pattern of vacuum fluctuations between them relative to outside them, and the difference in energy creates a pressure. The pressure is real. It has been confirmed in laboratories. The vacuum is doing something between those plates, and what it is doing is measurable. At the Planck scale, the suggestion, and it is a suggestion, a theoretical extrapolation rather than a confirmed observation, is that these fluctuations become so violent, so rapid, so geometrically extreme, that the concept of smooth space stops applying. The space-time that seems, at ordinary scales, like a continuous fabric becomes something more like static, like white noise, like the churning surface of water that from a distance looks like a flat plane but up close is nothing but turbulence. I am not sure I understand what this means. I don't think the field is sure either. What it might mean, for this chapter's purposes, is something like this. The nothing from which something appears to emerge in the expanding universe is not a passive nothing. It has structure, at scales too small to access. It has energy, measurable at the scales that can be measured. It has a ground state below which it cannot be pushed, a minimum activity that the universe does not permit to go to zero. The silence in a room is not silence. It is sound at a frequency you cannot hear, or in a register the ear does not process, or simply at an amplitude too small to distinguish from quiet. This is not a metaphor for the quantum vacuum. This is the closest available approximation of what the quantum vacuum is. The hum below the audible range, the motion below the resolution of the instrument, and the question that the foam raises, the question this chapter is walking past rather than through, because walking through it would require mathematics that these words cannot carry, is whether the energy of this ground state, the baseline vibration of every field in every cubic meter of space, is what is driving the expansion. The calculation says yes, obviously, of course it is. The calculation also says the number is wrong by 120 orders of magnitude. These two facts live together in the center of modern cosmology. The foam is real. The foam has energy. The foam's energy should be the cosmological constant, and the cosmological constant, as measured, is almost incomprehensibly smaller than the foam's energy should produce. Something is cancelling almost all of it. Nobody knows what. Go back up to the scale of the room. Let the Planck length be what it is, a distance that may never be directly measured, that currently sits at the edge of what physics can meaningfully say things about. The foam is still there. The vacuum is still vibrating. The ground state is still doing whatever the ground state does. The room feels still. The night is quiet. Between you and the ceiling, at a scale 10 billion billion times smaller than anything you can see, space is doing something that looks, from the theoretical vantage point, like everything happening at once, like every possible fluctuation trying to occur simultaneously, like a turbulence that by rights should tear the fabric it's occurring in. And from here, from this scale, from the scale of bodies and rooms and ceilings, it is indistinguishable from nothing. What this means for what this chapter set out to follow is that the nothing between things is layered in a way that only resolves into legible structure at one end of the scale, the cosmological, the vast, and hints at structure at the other end, the unimaginably small, in a way the current framework cannot yet fully read. The foam is real and unreachable and under everything. The surveyor's embarrassment. There is a specific quality to the moment just before a measurement is taken, when the instruments are ready and the analysis pipeline is set, and the question has been sharpened to its finest point, and everything that can be prepared has been prepared, and the only remaining thing is the number. That moment has a particular stillness to it, a suspension that is not quite confidence, and not quite doubt, but something sitting exactly between them. The awareness that the number is already somewhere determined, that the universe already has the answer to the question being asked, and that the asking is only the formality of receiving it. The teams that spent the 1990s measuring the expansion rate of the universe were in that moment, and the number they were waiting for was not the expansion rate itself, that had been known in rough form since Hubble, refined across decades to something called the Hubble constant, a measure of how fast the universe was pulling galaxies apart at a given distance. The number they were waiting for was something more specific, whether the expansion was slowing down, and if so, how fast. The expectation was rational. Gravity slows things that are moving apart. The universe is full of matter. Matter has gravity. Therefore, the expansion should be decelerating, the way a thrown object decelerates in Earth's gravity, at a rate that depends on the density of matter in the universe. Measure the deceleration, and you learn the density. Learn the density and you understand the geometry. Understand the geometry, and you know, among other things, whether the universe will expand forever or eventually collapse. This was the question. Measuring the deceleration was the method. The measurement required candles, not literal candles, but objects whose intrinsic brightness was known precisely enough to use as distance markers. At cosmological distances, you cannot use parallax, cannot use the familiar trigonometry of baseline and angle that works for nearby stars. You need something that shines with a known luminosity, something whose actual output is fixed, so that the observed brightness tells you unambiguously how far away it is. Dimmer means farther, in a relationship as clean as geometry allows. Type 1. A supernovae are what passes for a standard candle at those scales. They are the explosions of white dwarf stars that have accumulated enough mass to exceed a specific threshold, a threshold set by physics rather than circumstance, and the physics of crossing that threshold produces an explosion of remarkably consistent peak brightness. Not perfectly consistent, consistently consistent, with known corrections for the way they vary. Corrections that had been studied and calibrated across enough nearby examples that the community trusted them. They were the best rulers available for measuring distances in the billions of light years. Two teams spent years finding these supernovae in distant galaxies, measuring their brightnesses, calculating their distances, comparing these distances to the redshifts of the galaxies hosting them. The comparison would reveal the deceleration. The comparison would give the density. The comparison would, it was expected, confirm and sharpen what everyone knew was coming. The supernovae were too dim, not slightly too dim in a way that the error bars could not absorb, too dim in a direction that pointed in only one interpretation. The galaxies hosting them were farther away than they should be if the universe were decelerating. To be that far away given their redshifts, the universe could not be slowing. The universe was faster now than it had been when the light left. The expansion was accelerating. Both teams found this, independently, using different subsets of supernovae, different analysis methods, different people with different assumptions and different blind spots. The same answer emerged from both directions. The universe was not slowing. Something was pushing it, and pushing it harder as time went on, as the density of matter diluted with expansion, and the something that was pushing remained constant, and the ratio between them shifted further and further toward the push. The embarrassment was genuine and compound. It was not the embarrassment of having made an error. The measurement was right. The analysis was careful. The result has been confirmed by every subsequent method applied to it. It was the embarrassment of having asked a question whose answer required the immediate invention of a new category of physics. There was no shelf in the existing pantry for what the data required. A force distributed evenly through empty space, growing more dominant as matter diluted, with no identified source and no theoretical prediction in the right ballpark. This was not a refinement of the existing picture. It was a second picture, layered over the first, and the first picture had to be kept because it still worked at the scales it had always worked at. Both pictures are true. Neither picture contains the other. This is still the situation. The result was announced in 1998. The Nobel in Physics followed in 2011. In between, and in the years since, the observation has been confirmed from other directions. From the subtle temperature variations in the cosmic microwave background, from the clustering patterns of galaxies on large scales, from the way gravitational lenses bend light by exactly the amount consistent with the accelerating expansion model, from the statistics of how galaxy clusters have grown over cosmic time. The acceleration is real. The term describing it, dark energy, coined in 1998 to fill a naming gap, not a physical gap, has a measured value, a place in the standard model of cosmology, a parameter around which an entire generation of observations has been designed to improve. The precision is now high. The value is pinned to a few percent. The mystery is not smaller for being well measured. It is more precisely mysterious. Dark energy, at its measured value, accounts for 68% of the total energy budget of the universe. Ordinary matter, the atoms, the stars, the galaxies, everything that can be seen or detected directly, accounts for 5%. Dark matter, inferred from gravitational effects but not directly observed, accounts for 27%. The majority of everything is the thing whose existence was a surprise and whose nature remains, 25 years after the surprise, effectively unknown. The Surveyor's instruments were good. The Surveyor read them correctly. The land they revealed does not fit on the old maps, and the new maps, while accurate at the edges, have a very large blank space in the centre where the explanation should be. It's worth staying with the strangeness of this, the particular strangeness of having precise numbers without understanding. The expansion rate is known, the acceleration is measured, the fraction of the energy budget is constrained. the equations that use these values to predict the clustering of galaxies, the temperature spectrum of the early universe, the distances to remote supernovae, they work. They produce predictions that match observations to a precision that any field of science would regard as impressive. But the thing doing the majority of the work in those equations is a symbol, lambda, the cosmological constant, a number inserted because the observations demanded it, standing in for an explanation that has not arrived. Physics has had unexplained constants before. The fine structure constant, the number that governs the strength of electromagnetism, is precisely measured and theoretically unexplained. Constants accumulate in physics the way debts accumulate in households, slowly, with interest, and with the recurring promise that someday someone will sort them out. Lambda is a constant with an unusually large amount of universe behind it. 31% and 68%. You have been taught at some point that the universe is very large. That teaching is accurate as far as it goes. But it misses something. The universe is not just large in the sense of containing many things across a great distance. It is large in the sense that the space between the things is itself the majority of what is there, not the container, not the background, the main event. Here are the numbers, ordinary matter, the stuff of atoms, the substance of stars, the material in every table and planet and human body and dust cloud and galaxy ever observed, accounts for approximately 5% of the total energy content of the observable universe. 5, not 50, not 15, 5. Everything that has ever been seen, everything that glows or reflects or interacts with instruments, is a thin scum on the surface of something much larger, dark matter. The unseen gravitational scaffolding that holds galaxies together, that makes up the halos and the cosmic web along which ordinary matter congregates, adds another 27%. This matter is real, is present, is doing work every second. Nobody has caught it in a detector yet. That leaves 68%, and the 68% does not clump. It does not concentrate. It does not ride along the filaments of the cosmic web or gather in the halos of galaxies. It is in the void. Specifically, fully, completely in the void. The voids between galaxy clusters, the enormous empty volumes that make up most of the universe's volume, that have nothing luminous in them, that are defined by the absence of visible structure. Those are where dark energy lives. If leaves is a word that can apply to something that does not do anything in particular, except be present at a constant density and push. Think about what a void actually is, not in the metaphorical sense, physically. The voids between galaxy clusters are not small. They range from tens to hundreds of millions of light years across. They are regions where the large-scale structure of the universe, the cosmic web of filaments and clusters, gives way to something close to a genuine absence of ordinary matter. A galaxy wandering into a void would find no neighbours in any direction it could reach with light in a human lifetime. The nearest structure would be, in any meaningful sense, unreachably far. These volumes are enormous, and they are the majority of the universe's volume. Surveys suggest voids account for roughly 80% of space by volume. The bright, structured, galaxy-rich filaments and clusters are edges. The voids are the faces of a foam made of almost nothing, and those faces go on and on. In all of that volume, in the centre of the voids and at their edges and in every part of them, dark energy sits at its constant density. Not a trace of it. All of it. 68% of the energy of the universe spread across 80% of its volume, which means the typical cubic meter of this universe is mostly dark energy and mostly void, and mostly nothing a human instrument has yet found a way to point at directly. The pie chart version of this: 31% matter, 68% dark energy, rounding errors, is a thing that can be stated in a sentence and absorbed in a second and then immediately lost. The numbers are too clean. They are the kind of numbers that fit on an infographic and do not convey what they are saying. What they are saying is, when you look at the night sky and see the stars and galaxies and the beautiful structure of the observable universe, you are looking at 5% of it. The rest is dark. The rest is, in one form or another, beyond what the eye and most of its extensions can access. The universe that is spoken about in casual science communication, the one with the galaxies and the nebulae and the elegant cosmic web, is the trim on an object whose bulk has not been described yet. The trim is beautiful. The trim is everything that has ever been mapped. But 68% is in the blank space, spreading out, growing its share of the total with every second the expansion continues, and it does not care about the trim. A candle held at the edge of everything. There is a way of describing stars that is probably familiar. They are distant, they are hot, they are made of the same elements that make everything else. They were not there, and that they were, and eventually they will not be again. This description is useful. It places stars in the inventory of things that exist and change. It misses what it feels like to use a star, to use a specific kind of stellar death as a ruler long enough to measure the universe. The ruler exists because of a physical coincidence so exact it seems deliberate, though it is not. When a white dwarf star, the dense remnant of a sun-like star after it has exhausted its fuel and shed its outer layers, accumulates mass from a companion, from a donor star near enough that its material can fall inward, there is a threshold. The mass cannot grow past approximately 1.4 times the mass of our Sun without triggering a thermonuclear explosion that destroys the white dwarf entirely. The threshold is not a range. It is a number that physics sets without negotiation, and the explosion that results from reaching it has, for all observed cases, a peak brightness that can be normalized and calibrated to a standard. Type 1, a supernova. That is the name. The name was used once in Chapter 6. Here it is, the instrument, the ruler, the only available stick long enough. The brightness arrives at the telescope. The brightness is compared to what the explosion should have produced. The ratio gives the distance in a way that no other object at those scales can give it. And the distance, compared against the redshift of the galaxy the explosion was in, the redshift being a measure of how much the universe has expanded since the light left, yields a relationship, a curve, a shape that describes the expansion history of the universe, the way a heart monitor traces the history of a heartbeat. Teams in the 1990s were reading thousands of these curves, calibrating them, cleaning them. Each curve came from an explosion that had already happened before a single human was alive to see it, sometimes before the Earth had formed, sometimes in the first few billion years of the universe. The light only now arriving, after a journey of billions of light years, hitting a detector designed to catch exactly this kind of ancient news. The ancient news was not confirming the expected curve. Expected. The curve bends downward. Distance grows as you go back in time, as you look at more distant, more ancient explosions, but grows more slowly than it would if the expansion rate had been constant, because in the early universe, when matter was denser, gravity was pulling harder on the expansion, and the expansion was decelerating. Closer objects appear brighter than they should be in a constant rate expansion. More distant objects are dimmer than they should be, but not too much dimmer, and the shape of the dimming tells you exactly how hard gravity was working. Observed, the curve bends the other way. The distant explosions were dimmer than the expected curve predicted. Not slightly, clearly repeatedly, in data clean enough to survive two independent teams checking it against each other. Dimmer means farther. Farther means the universe had expanded more than expected by the time the light reached us. More expansion than expected means the expansion was faster then, or equivalently is faster now, than a decelerating model predicts. The curve was the wrong shape, and the only way to make the curve the right shape, the only modification to the standard cosmological model that could turn the observed curve into the expected one, was to add something that was not in the model, a term, a constant, a thing distributed through all of space at constant density, with negative pressure, pushing the expansion faster as the density of matter diluted and the push-to-pull ratio shifted. Dark energy. The constant returned. There is a quality to evidence that comes from very old light. It is not more reliable, necessarily, than evidence from nearby things. The corrections and calibrations required are extensive, and each step introduces uncertainties that must be tracked and managed. But it has a particular kind of weight, the weight of distance, of the information having travelled so long to arrive. When the light from an explosion 10 billion light-years away hits a pixel in a charge-coupled device on a telescope in Chile, the information it carries left its source before the solar system existed. It has been travelling for longer than the Earth has been a planet. This light was already on its way when the oceans formed. It was somewhere in intergalactic space when the first cells divided in the first shallow seas. It was closing the distance while the dinosaurs lived and went and while everything after them happened. It arrived in a data file, was processed by analysis software, appeared as a point on a plot, and the point was in the wrong place. And the wrong place meant the universe was not doing what gravity alone would do. That is what a candle held at the edge of everything tells you. Not warmth, not light. A data point, a wrong data point, a wrong data point that turned out to be right. The thing that doesn't dilute. The expansion is happening now, this second. Not as a fact to hold at a distance, but as something occurring in the space this sentence occupies, in whatever room is hosting this sound, in the distance between this page and the wall, and the distance between this building and the next galaxy, and the distance between that galaxy and the next cluster of galaxies, and all the way out, in every direction simultaneously, in the dark between the structures that have been described across the previous 8 chapters, right now. The space is larger than it was when you started this sentence. Most things spread when they are given more room. This is thermodynamics, which is a formal way of saying what experience already knows. Heat disperses, gases expand, concentrations equilibrate, differences smooth themselves out. You open a hot oven in a cold kitchen, and the warmth doesn't stay in the oven. It moves into the kitchen. into the living room, up through the ceiling, diffusing outward until the temperature difference that made the oven distinct is gone. Everything tends towards sameness, toward the spread out, toward the lower concentration that more volume allows. Dark energy doesn't do this. Here is the thread from the inside. As space expands, the density of everything in it drops. Ordinary matter, fewer atoms per cubic meter as the cube grows. Radiation. The energy density of photons drops even faster, because not only does the number of photons per volume decrease, but each photon also redshifts, loses energy, as the space it's travelling through stretches. Dark matter dilutes with expansion, same as ordinary matter, slower than radiation. Everything thins. Dark energy, constant. Measure the energy density of the vacuum today, and it is approximately 6 times 10 to the power of minus 10 joules per cubic meter. This number is very small. It is the energy equivalent of about 4 hydrogen atoms per cubic meter of space, which is already an almost empty space. But measure it 1 billion years from now, and it will be the same number, in the same units, per the same cubic meter, even though that cubic meter will have expanded, and 1 billion years after that it will be the same again. This is not a numerical coincidence that resolves if you look at it differently. This is the defining physical property of whatever dark energy is, the property that makes it unlike every other substance in the universe's inventory, the property that causes it to grow as a fraction of the total energy budget as expansion continues, the property that means eventually, given enough time, there will be essentially nothing but dark energy and the slow remnants of matter in the dark. If you are inside this process, and everything is, there is nowhere outside it. The sensation of it is not like acceleration. It is not like being pushed. There is no wind, no force pressing against the body, no sense of motion the vestibular system could register. The expansion of space is not movement through space. It is the growth of the distance between things. It is the metric, the relationship between points, changing, while each point remains, locally, where it is. What this means, from the inside, is something closer to separation than to travel. The galaxies are not flying away from each other across a fixed background. The background itself is growing. If you were sitting in the intergalactic void, in the middle of nothing equidistant from the nearest galaxy cluster in every direction, you would feel nothing, no wind, no pressure. The local physics would be entirely ordinary. You would measure the quantum vacuum fluctuating at its usual rate, the ground state energy of all fields present at its usual density, the temperature of the cosmic microwave background at its current value. The expansion would only be detectable by looking outward and noticing that the distant clusters were receding at a rate inconsistent with any local force, and then waiting and looking again and noticing they were receding a little faster than before, the rate itself growing as dark energy's fraction of the total grew, as the ratio between its constant density and the diluting matter shifted further in its favour. This is what the void is doing, quietly, from the inside, in a way that nothing inside it can directly feel. The thing that does not dilute is, at current measurements, roughly as energetic as the thing that does. The ratio changes continuously. Dark energy's fraction grows as matter dilutes. But right now, as a present epoch of cosmic history, we are in a moment of approximate balance, the transition period between a matter-dominated universe and a dark energy-dominated one. From here on, dark energy wins. The ratio will never return to matter dominance. There is no mechanism to restore it. This transition has been happening for approximately 5 billion years. It will continue for the remainder of the universe's duration, which is very long. In the far future, in the cosmological sense, in billions and then trillions of years, the matter will be so diluted and the dark energy so dominant that the universe will be, in terms of energy, almost entirely the constant, the vacuum, the thing that doesn't dilute. It will be, by overwhelming majority, nothing. Nothing that has a specific energy density per cubic meter. Nothing that is still expanding. Nothing that will be, by that point, expanding so fast that the observable universe will have shrunk to a bubble smaller than a galaxy, then smaller than a solar system, then smaller than a planet, as the horizon recedes faster than light can cross it. A very dense nothing, but that's later. Right now the expansion is just this, quiet, constant, the fabric giving slightly in every direction. The something that doesn't spread staying steady in every cubic meter it creates. The void adding to itself without subtracting from what was already there. The room is larger than it was. You would never know. What emptiness costs? The calculation has been performed many times by many physicists, each time with slightly different approaches and slightly different levels of rigor, and each time producing the same essential result, which is that the result is wrong by more than any result in the history of science has ever been wrong. This is worth dwelling on before the specific numbers arrive, because the numbers, when stated, can be absorbed too quickly. Processed as large, filed under incomprehensible, and set aside in the way that incomprehensible things are set aside. What resists this filing is the context. Physics is, in general, very good at making predictions. The standard model of particle physics predicts the magnetic moment of the electron to 10 significant figures, and the measurement agrees to 10 significant figures. The calculations of nuclear structure that allow physicists to predict the binding energies of atomic nuclei are precise to fractions of a percent. General relativity has passed every experimental test it has been subjected to for a century, including the measurement of gravitational wave frequencies from merging black holes billions of light years away, to a precision that would embarrass most engineering. Physics does not generally get things very wrong. When it does, it means something fundamental is missing. The calculation in question is for the energy density of the quantum vacuum, the same ground state energy of all fields that appeared in the chapter on foam, the baseline vibration that cannot be removed, the energy that the Casimir effect demonstrates exists, and that quantum field theory provides a recipe for estimating. Sum up the 0-point energies of all known fields up to some cut-off scale, and you get a number. The cut-off scale matters. You have to stop the calculation somewhere, because integrating to infinite energies gives infinite answers, and infinite answers are not useful. Physicists typically stop at the Planck scale, the scale at which quantum gravitational effects should become important, the scale at which the smooth geometry picture breaks down. The number that comes out is approximately 10 to the power of 113 joules per cubic meter. The number measured by observation, the cosmological constant, the energy density of dark energy, as determined by the supernova surveys and the microwave background and all the other methods that converge on the same value, is approximately 6 times 10 to the minus 10 joules per cubic meter. The difference between these two numbers is a factor of roughly 10 to the 123rd power. There are large numbers in physics. The number of atoms in the observable universe is approximately 10 to the power of 80. The number of Planck times in the current age of the universe is approximately 10 to the power of 61. These are large numbers that arise naturally from the scales of physical objects and the constants governing them, and they are understood, not comfortable exactly, but understood in the sense that their origin can be traced. The number 10 to the power of 123 is the ratio between what the vacuum should weigh, by the best theory available, and what it actually weighs, as measured. This is not a number that arises from any natural scale in physics. It is a discrepancy, a gap between the predicted and the observed that is larger than any other gap in science by many orders of magnitude. Something is making the vacuum nearly weightless by the standards of its own activity. Something is cancelling nearly all the energy that the fields in the vacuum should be contributing to the cosmological constant, leaving only the tiny residue that has been measured. A residue so small relative to the individual contributions being cancelled that achieving it by accident, by some arbitrary cancellation of unrelated terms, would require a precision that has no physical mechanism to explain it. This is sometimes called the cosmological constant problem, and sometimes called the vacuum catastrophe, and both names are accurate. There are proposals for why the cancellation might occur. Supersymmetry, a theoretical extension of the standard model that pairs each known particle with a partner of different spin, was once hoped to provide the cancellation mechanism. If the contributions of particles and their supersymmetric partners cancelled each other exactly, the vacuum energy could be naturally small. But the supersymmetric partners, if they exist, should have been found at the Large Hadron Collider by energies the machine has already reached, and they have not been found. Supersymmetry has not been ruled out entirely, but its simplest and most appealing versions, the ones that would most naturally solve the cosmological constant problem, are now disfavoured by the absence of evidence. There is a proposal involving the anthropic principle, the argument that we observe the cosmological constant we do because a significantly larger value would have caused the universe to expand too rapidly for galaxies and stars and planets and observers to form, and so any observer capable of measuring the constant will find it in a range compatible with their own existence. This argument is controversial in ways that go beyond what can be fairly resolved in a chapter of a science narration. It is true that a much larger cosmological constant would have prevented structure formation. It is unclear whether that constitutes an explanation. There are proposals involving additional fields, additional dimensions, modifications to gravity, ideas that go by names like quintessence and modified gravity, and loop quantum cosmology, each with adherents and critics and a track record of predicting things that observations have not yet confirmed or refuted. I am not sure which of these, if any, will eventually resolve the problem. I am not sure any of them have the right shape yet. This is not false modesty. The field genuinely does not have a consensus candidate. What the problem points toward, this is the sediment that has been accumulating across this chapter, the layer this paragraph sits on top of, is a gap not just in the calculation, but in the framework doing the calculating.
Quantum field theory and general relativity are the two most successful physical theories ever developed. They each predict things correctly to extraordinary precision within their own domains. They are also fundamentally incompatible when applied to the same regime, specifically the regime where quantum effects and gravitational effects are both relevant. The Planck scale, the scale at which the foam of the previous chapter lives. The cosmological constant problem lives at exactly this interface. The vacuum energy that quantum field theory produces is, in quantum field theory, a number. In general relativity, energy has gravitational consequences. All energy does, including the energy of the vacuum.
When you take the quantum field theory number and ask general relativity what it implies for the curvature of space-time, you get a universe that expands so fast it immediately tears itself apart. That is clearly not the universe. Something, somewhere between the quantum calculation and the gravitational consequence, is not working the way it should be. The theories do not know how to talk to each other. The cosmological constant problem is what you see when they try. This chapter has accumulated several things without resolving them, which is the honest shape of the problem. The calculation exists. The immeasurement exists. The gap between them is 10 to the power of 123. The mechanism that closes the gap is not known. The deeper incompatibility that the gap likely reflects between quantum mechanics and gravity is not resolved. The universe, meanwhile, is expanding at exactly the rate the small measured number predicts, oblivious to the argument about why that number is what it is. The vacuum weighs almost nothing by the standards of its own activity, and it is doing this correctly, reliably, measurably, across the entire observable universe, and nobody knows how. This is not a failure of knowledge that more experiments will straightforwardly correct. It is a sign that the map has an edge, and beyond the edge is territory the current instruments were not built to navigate.